Now this is a interesting problem, something related to aromatic substitution, but this time nucleophilic aromatic substitution. So let us copy this one first and then we'll discuss why this is happening, what is the problem. So this is 17.23, of course taken from, as I remember this has been taken from LG Bade or Solomon, I don't remember. I think this problem I have taken from LG Bade. Okay, let us copy this one and then we'll discuss what the problem is all about. So you have a benzene ring that contains two nitro group. If you remember something, a benzene ring contains too many deactivating group. In that case, nucleophilic substitution becomes easy because on benzene ring nucleophile attacks only if there are so many deactivating groups are attached. If you have many deactivating groups attached in the benzene ring, what happens? Nucleophile can attack easily because benzene ring having less electron cloud. So electron clouds are basically distracted by this deactivating group. So now this reaction says, so this is a nucleophilic substitution reaction. You see what is happening. You have RNH2. This RNH2 gets attached here. So this seems like this attacks here and fluorine goes. You will have here. And if you release one H plus from here, then you will also get one compound HF. So you will get HF is another product, that is an inorganic product. Now see, we have said earlier in a groups, if you go down, the leaving group ability increases because minus charge becomes more stabilized. So fluorine is not a good leaving group. Chlorine, bromine, iodine is a good leaving group. So I can say F minus is not a good leaving group or a poor leaving group for SN1 and SN2 reaction. If you remember what happened in SN1 and SN2 reaction. In SN1 also there is a carbon and leaving group that breaks. So if you see SN1 reaction, this bonds break, carbon and leaving group. Even if you take SN2, carbon and leaving group breaks. In both cases you see there is a breaking of carbon and leaving group. Are you getting? Now that is the basically answer of this question, so I will not elaborate more. So let us go to the question. F minus is a poor leaving group for SN1 and SN2, of course, because this bond breaks, this bonds break. If this is not a good leaving group, then SN1 and SN2, rate of SN1 and rate of SN2 will decrease. Why this reaction happen? But you see, F minus, even F minus is a poor leaving group. SN1, SN2 does not occurs in this case. But why this nucleophilic substitution occurs in this case, even though fluorine minus is not a good leaving group? Are you getting my point? What I want to say is, F minus is not a good leaving group. This means, if I want to do a substitution on alkyl halide, I should not take RF because this is not a good leaving group. This bond is a strong bond. So any nucleophile can attack, but this cannot leave. And that's why if I want to do SN1 and SN2, I cannot take fluorine as a leaving group. Are you getting? But here we have fluorine is a leaving group, but substitution, nucleophilic substitution is happening. Why this is so? Now I will give you a hint. To see whether the reaction happens or not, I have to look the RDS step, mechanism rate determining a step. You see, in nucleophilic SN1 reaction, first state is, if you have SN1, what is the first step? Loss of leaving group. That is, the leaving group comes into the RDS because loss of leaving group is the RDS step. If the reaction is SN2, both happen same time, this attacks, this goes. Once again, this leaving group comes into the picture, RDS. That is enough hint. So if you have SN1, leaving group come into the picture. If we have SN2, leaving group come into the RDS. So in both cases, leaving group comes into the RDS. But why this reaction is happening? So if SN1, SN2, leaving group comes into the picture, so this means a poor leaving group will decrease the rate. But here I have the reaction. This means rate is even faster in this case. Why this is happening? So I have given partial answer. Now you have to think yourself. Most of the answer is given. So let us wait for 2 minutes. If you want, you can discuss with your friends also, no problem. If you can do your own, that's fine. That's the best thing you can do. Okay, let us see the solution. So, if we have, so the same thing can be answered in this way. If you have the nucleophilic, aromatic nucleophilic substitution, you will have something like this. What will happen? Nucleophile will attack here and this bulb won't open. So you see, so let me write here. You have fluorine here and then you have nucleophile. This nucleophile will have a lone pair, so this attacks here. This goes here. So you will get the same thing. Are you able to see or not? Okay, good. So you see, if you do something like this, there is a nucleophile carbon bond. So nucleophile carbon bond you will have, and this minus charge. And this minus charge will be resonance stabilized. Now if you have either SN1 or SN2, you will have something like this. If you SN2, nucleophile attacks, this goes. So if this is the case of SN2. If we have SN1, in that case, you will have fluorine here. So this ball will break. So this is a case of SN1. Are you getting? So this is a case of SN1. Let us call this a C. This is a case of SN2. And this is a case of addition elimination reaction. So this is a case of addition elimination. So this is a case of addition elimination. Are you getting? So you have three situations. If you have addition elimination, you will get the transition state or intermediate A. If you have SN2, you will have something of this kind of a step. Nucleophile is attacking, this is going. This is the RDS. So in RDS, nucleophile is attacking, this is going. So this is the critical part we are discussing. In SN1, if you have SN1, this bond is breaking. So now see, if you have SN1, the breaking of bond comes into the picture. If you have even SN2, breaking of bonds comes into the picture. But if you have addition elimination reaction, fluorine breaking does not comes into the picture. In this case, the stability of carbon ion is solely guided by this aromatic compound. So this is resonance stabilized. So F minus does not comes into the picture. Are you getting? So I can say formation of this complex is the RDS. In this case, these are the RDS. So if you want, you can write. So formation of anionic sigma complex is RDS. Loss of F minus comes later. So for case A, so this is for B and C. Let us say this is for B and C. Okay, first write. For A, what we have, formation of anionic sigma complex is RDS. Loss of F minus comes later. You see what will happen. This is this you have now. So let me see here. So this is, and then you write, just don't worry. So you have fluorine here and nucleophile here, and here you have a minus charge, or you can have what I have written earlier. You can see if you have confusion, then you can take the same thing. You have a minus here. Are you getting? And now what happens in the next step? You can write down the resonating structure. This goes here and this fluorine goes out. This is the only case. Are you able to understand or not? Should I draw the next structure, or are you able to understand? Assume that you are able to understand. Let me draw once again if you are not able to understand. So this molecule you have fluorine here, you have nucleophile here. Now this lone pair goes here and this goes here. So this is the second step. First step is attack. This step is a faster step because this gains the aromaticity. So this step is a faster step. So first step is complex of anionic sigma complex. If I call this is a anionic, because anion, and this is called sigma complex. So this is a anionic sigma complex. Have you written? So if you see, formation of anionic sigma complex is RDS, but loss of F minus comes later. If I make the potential energy diagram, don't see this one. Let us first read this diagram. So it will come something like this is the first step, this is the second step. Second step is a faster step, first step is a slower step. And that's why F minus does not comes to the picture. So F minus does not affect the rate of reaction because the second step, first step. If you cross the first step, second step is always over because it's the first step. So F minus, even though it's not a good leaving group, in the second step it comes because that is second step is a faster step. F minus does not decreases the rate of this reaction. But if we have case B and C, in SN1 or SN2, carbon fluorine bond breaking comes into the picture, comes into RDS, and that's why the rate is slow. If you see for SN1 and SN2 RDS, so this is for SN1, this is for SN2. F minus bond breaks here, so this comes into the picture. F minus comes here, also F minus come because F minus leaves. So in both cases SN1 and SN2, F minus comes into the picture. But in case of nucleophilic addition elimination reaction, this does not come into the picture, and that's why all the things happening. So you can copy this one. I think you have written. Okay, so let us write this one. Have you copied or not? So if you have not copied, let us copy. So basically we don't have so much advanced camera, and that's why we are not able to show you properly. Maybe in future we can have a good camera. Although even these days video cameras are coming very cheap, but still it's costly for us. We cannot afford so much costly cameras. Maybe in future we will have. Okay, let us make something like this. This is slightly, you maybe see the picture is basically oxidating. Done? I think you have done, no? Okay, go for the next problem.